Hey guys, this is Cheyenne and today I'm gonna talk about induction using Hey guys, this is Cheyenne and today I'm gonna talk about induction using dominoes. Okay, so assume that I want to just arrange these dominoes in a way that after I push the first domino, all of them will fall. Assume that I wanna just make sure that all of them will fall. Well, how can I prove that based on my arrangement, all of them will fall? So, I mean, how exactly can I be sure about it? How can I be sure that, okay, if I put all the dominoes like this, after I will push the first one, all of them will fall. How can I prove this? How can I prove that for each domino it will fall? Well, the good news is that there's an easy way to prove that. Well, while I'm arranging this, I just try to arrange it. I just arrange the first one at a place and I know that I will push this one. Okay, so I will put first one in the first place and I know that it will fall because I will push it. And then I will put the second one in a way that I'm sure that if the first one falls, the second one will fall. So after that, I will just put the second one in a way that if the first one falls, this one falls as well. So I just care about the distance between these two first dominoes and nothing else. And then when I put this black one, I just put it in a way that I can be sure that if this red one falls, then this black one falls. I don't really care about anything about the previous dominoes. I'm not even saying that the red one really falls. I'm just saying that if the red one falls, then the black one falls. If the second domino falls, then the third domino will fall. And after that, I have another domino. And I'm saying that if this black domino will fall, then this green domino will fall. If the third domino will fall, then the fourth domino will fall. And the fifth domino as well. If this green one will fall, then this one will fall. So the idea is that I'm making a chain like this. I'm just saying that about the first one, I know that it will fall. Okay, I will push it. About this, and then I will make a chain. I say that if the first one falls, then the second one falls. If the second one falls, then the third one falls. If the third one falls, then the fourth one falls, and so on. So the whole thing that I'm saying in here is that if the domino number k will fall, it's an assumption. I don't want to prove that the domino number k falls. I'm just saying if domino number k falls, then domino number k plus 1 falls. That's the whole thing. And then that's the fact that the domino number 1 falls is like our base. You know, the first one is like our base. I know that the first one falls, so I need to have a base. But this chain is just our inductive step. So I'm just saying that if this one falls, if the number k falls, then the k plus 1 will fall. So I'm just making this chain and I don't really need to prove that domino number k will fall. It's just an assumption. It's a fucking assumption. I don't really need to show that the domino number k will fall. I most of time see people asking that, yes, but why domino number k will fall? Why it is true for k? You don't need to prove that. It's an assumption. It's an assumption that if this one falls, then this one will fall. Then why this one falls? Because we know that if this one falls, then this one falls. Then why this one falls? Because we know that if this one falls, this one will fall. Why this one falls? Because we know that if this one falls, this one falls. And why this one falls? Well, this is our base. We will push this. So the whole idea is that we do not really need to prove that the domino number k will fall. Our step is assuming that domino number k will fall. Then we show that the one number k plus 1 will fall too. So this is a fucking assumption and nothing else. You don't need to prove this. You don't need to prove that it is true for k. You're just saying that if something is true for k, then it is true for k plus 1. It's like, for example, if it is raining today, I'm gonna wear that dress. And then when tomorrow, if it is not raining, then you won't wear that dress. It's okay. It's just an assumption. If it rains, you will wear that dress. So we're just saying that if it is true for k, then it is true for k plus 1. If you had to prove that it is true for k, then what was the power of induction? How was it useful? I mean, okay, if you can show that for k it works, then you have showed that for any k it works. I mean, you don't need anything else. The power of induction is induction hypothesis, is that you assume that it is correct for some k, and then assuming that, you just show that it is also correct for k plus 1. When I want to arrange these dominoes, I don't really need to prove for each domino that it will fall. I can just assume that, okay, assume that the previous one will fall. Just assume that. I'm just making sure that if this one falls, then this one falls as well. This way I'm like forming a chain. I'm just saying that the first one ensures that, for example, the second one will fall. The second one ensures that the third one will fall. The third one ensures that the fourth one will fall, and so on. Okay, I might have many more and again say the exact same thing. Okay, so I'm just making a chain and I'm saying that each one ensures that the next one will fall. So I can just, if I do this, all of them will fall. And this way, by forming this chain, then I have proved something for everything, for all the numbers, for all the dominoes, for anything. So if I just show that for the first one it is true, and if for each one it is true, then for the next one it's true. If this domino falls, then this domino falls, then I can show that all of them will fall, or it is correct for any number. Okay, so don't forget that this k, you do not have to prove that. If you had to prove that, why using induction? What is the benefit of using induction then? I mean, if you can prove this for any k, then you can prove it for any k, so it is proved already. So how does induction help you? The whole point is that you can assume that it is correct for k, and just trying to form this chain. You can just try to form the chain. If it is correct for 1, then it is correct for 2. If it is correct for 2, then it is correct for 3, and so on. If you show this, then it's only enough to show that it is correct for the first one. When you show that it is correct for the first one, then it is also proved that it is correct for everyone, because once every one of them falls, it ensures that the next one will fall. And then you're sure that all of them will fall, and it is proved for all of them. Okay? So that's basically the main thing in here. So don't forget that. I'm saying for the 100th time. You don't really need to prove it for k. You can just say that if it is true for k, then it is true for k plus 1. Or you can instead say that if it is true for k minus 1, then it is true for k. Both of them works. I mean, they're the same thing. I'm saying that if for this number it is true, then for the next number it is true. That's the whole thing. Okay. Now let's see this. Now let's consider some examples and see if we can solve some problems using induction. Assume that I want to prove that n factorial is greater than 2 to the power of n for any number n greater than or equal to 4. Okay, so I want to show that for any number n greater than or equal to 4, n factorial is greater than 2 to the power of n. Well, first try to form the chain in here. Most of them you start with base, but here let's just first form the chain and we see what we're talking about. Assume that for n equal to some value k, it is correct. What does it mean? It means that k factorial is greater than 2 to the power of k. Okay? Assume that for k is okay. It's an assumption. You might ask how did we show that it is true for k? It's an assumption. I'm just saying assume that it is correct for k, okay? So we assume that it is correct for some k. Then we show that if it is true for k, if it is correct for k, if it is correct for k, a hypothesis, then it is correct for k plus 1. How do we say that? We can say that, okay, k plus 1 factorial is equal to k plus 1 times k factorial. 2 to the power of k plus 1 is equal to 2 times 10 to the power of k, right? So it's like in one side we have k plus 1 times k factorial, and on the other side we have 2 times 2 to the power of k. And we want to compare these two. And we know that we are just proving for n greater than or equal to 4, so our k is at least 4. We just care about 4, 5, 6, 7, 8, 9. So our k is only 4, 5, 6, 7, 8, 9. We don't care about 1 or 2 or 0 or minus 5. We just care about 4, 5, 6, 7, 8, 9. So we know that k plus 1 is greater than 2. Also, k factorial is greater than 2 to the power of k. Why k factorial is greater than 2 to the power of k? That was our assumption. We just said that if k factorial is greater than 2 to the power of k. So it's just our assumption. We know that this is greater than this, and also this number is already greater than the other number, and it is also multiplied by a greater number. So it still will be greater than the other number. Period. So we have proven that it was greater than the other number, and it is now multiplied by a greater number as well. For example, when it is correct for 4 factorial is greater than 2 to the power of 4, then the next time this one will be multiplied by 5 when it becomes 5 factorial. This one will be multiplied by 2 when it becomes 2 to the power of 5. So this one is already greater than this one, and it will be multiplied by a greater number 2. So obviously it is going to be greater than the other number at the end. So the chain is formed. We just showed that for any value of k greater than or equal to 4, if it is correct for n equal to k, then it is also correct for n equal to k plus 1. If it is correct for n equal to k. So now I have this chain. 4, if 4 is true, then 5 is true. If 5 is, then 6 is. If 6 is, then 7 is, and so on. And this chain will be continued forever. Now, if I just show that this was also correct for 4, then I have proved that it is correct for any positive integer greater than or equal to 4. And why it is true for 4? Because 4 factorial is 24, and 2 to the power of 4 is 16, and 24 is greater than 16. So for 4 it's true, because for 4 it's true, for 5 it's true, because for 5 it's true, for 6 it's true, because for 6 it's true, for 7 it's true, and so on. So for every integer it's true. So I formed this chain that if for k is true, then for k plus 1 is true. And then I showed that for the first one is true. So if these dominoes had some numbers, for example, this one was 4, this one was 5, this one was 6, this one was 7, this one was 8. Each one of them, we showed that if this one for this one, okay, For example, this one is 7. If for 7 it is true, then for 8 it's true. If for 8 is true, then for 9 is true. If this one falls, then this one falls. And so on. Okay, so we continue like this. We showed that if for each one is true, for the next one is also true. And if this one falls, the next one falls. We just ensure that the distance between each two is in a way that if the previous one falls, this one falls as well. So now if I just push the first one, if I just show that for 4 it's true, 4 will ensure that for 5 it's true. 5 will ensure that for 6 is true. 6 will ensure that for 7 is true. And so on. So everything I'm sure that they are true, or every domino will fall. So that's all about induction. That's the general idea behind induction. Now let's solve two harder tasks using induction. Well, now consider that we want to prove that 1 plus 2 plus 3 plus 2n is equal to n times n plus 1 divided by 2. Gauss. Okay, this is a well-known equality. Okay. How can I show that? Well, first I show with my base, inductive base. What my base can be? Well, base can be both 0 or 1. Both works. I can both say that for n equal to 0 it works, or for n equal to 1 it works. 0 is even easier. For n equal to 0, the left part is empty, so it's 0. It's sum of nothing, so it's 0. The right part is also 0 because it's 0 times 1 divided by 2. So it is correct. For n equal to 1, this is okay. Now we need our step. Our inductive step, it's gonna be like this. We just say that if for some n equal to k, k greater than or equal to 0, k is an integer greater than or equal to 0, if it is correct, then for n equal to k plus 1, it is correct. How do I show that? Well, I just consider these numbers 1 plus 2 plus 2k plus 1. I'm saying that this is gonna be equal to the sum from 1 to k plus this k plus 1. And I know that based on my hypothesis, this value is equal to k times k plus 1 divided by 2. Why? Where did I show that this is equal to k times k plus 1 divided by 2? Well, it's a fucking hypothesis. I'm just saying that if it is correct for k, then it is correct for k plus 1. I'm not saying that it's correct for k. I don't fucking care if it is correct for k. I'm just saying that if it is correct for k, then it is correct for k plus 1. Okay, that's it. I'm just saying if it is correct for k, then it is correct for k plus 1. So this is my hypothesis. I'm just assuming that it is correct. I'm just assuming that from the sum from 1 to k is equal to k times k plus 1 divided by 2. This is my assumption. Okay? So this is what I have, k times k plus 1 divided by 2, and I have to add k plus 1 to it. And what is k plus 1? I'm just saying that this is equal to k times k plus 1 divided by 2 plus 2k plus 1 divided by 2. Well, k plus 1 is equal to 2k plus 1 divided by 2. Okay, it's nothing. And then it's like I have k plus 1 times, from here I have k, from here I have 2. K times k plus 1 plus 2 times k plus 1. Okay, k times k plus 1 plus 2 times k plus 1. The sum of them is k plus 2 times k plus 1, right? Divided by 2. Both of them have division by 2. So I showed that if it is correct for k, it is also correct for k plus 1. So this is okay. Okay, so my chain is formed as well. I just showed that if for 0 it's correct, then for 1 it's correct. If for 1 it's correct, for 2 it's correct. If for 2 it's correct, for 3 it's correct. And so on. So my chain is formed. And then I just need a little push for the first domino. I just say that for 0 it is correct. For 0 both sides are 0. Okay. For 0 both sides are 0. So for 0 it's correct. When for 0 it's so correct, then for 1 it's correct. When for 1 it's correct, then for 2 it's correct. And so on. So this is the way that you can prove this equality using induction. Okay, that's it. Now let's consider the last example, a harder problem and more interesting problem. Assume that we have a grid. We have a 2 to the power of n by 2 to the power of n grid. And assume that n is at least 0, for example. So if n is equal to 0, 2 to the power of n times 2 to the power of n is a 1 by 1 grid. It just has one cell. Okay, so it's like this. For example, in this example, we have a 4 by 4 grid. So we have a 2 to the power of n by 2 to the power of n grid. And we say that one of the cells is blocked. One of the cells is blocked. You have to prove that we can cover the rest of the cells using this shape. And we can rotate it as we want. We can rotate this shape as we want, and that's okay. But we have to use several of them such that it will cover all of the cells. Okay. And by covering, I mean that each of the cells should be covered exactly once. Okay, I mean you cannot have two of these shapes such that both of them cover the same cell. For example, in here, the first one can cover these 3 ones. The second one can cover these 3 ones, these 3 ones, these and this. You see that each of the cells is covered exactly once. Okay, is covered by exactly one of these. Okay, this is what we say when you say it should cover everything and exactly once. Okay, so how can we prove that? This problem is more interesting now, right? So again, let's start with the inductive base. Okay, inductive base. Our base can be, for example, 1. If our base is 1, then it means that we have a 2 by 2 and one of the cells is blocked. Okay, so we obviously can cover the rest of these cells, the other 3 cells, using one of these shapes. So for n equal to 1, it is correct and we're done. But there is an easier way for the base, right? Forget about n equal to 1 and just prove that for n equal to 0. For n equal to 0, you have only one cell and one cell is blocked, so that cell is blocked. You have to say that you can cover all the remaining cells. Well, there's no remaining cell. You have to do nothing. Everything is fine. So it's proved already. Because n is 0, you have a 2 to the power of 0 by 2 to the power of 0 grid. So it's a 1 by 1 grid. So it has one cell and that cell is blocked. So it is covered completely. There's no remaining cell and you have to do nothing. So for n equal to 0, it's obvious that it is correct. And now we have to form that chain. Now we have to consider that it is correct for n equal to k. And now we want to show that it is correct for n equal to k plus 1. So we assume that if we have a 2 to the power of k by a 2 to the power of k and any of the cells is blocked, that can be any cell. We just know that one cell is blocked. There's no additional constraints. One cell is blocked. So we know that if it is like this, we can somehow put these shapes in a way that it will cover all the remaining cells. We just assume that that is correct. You might ask why? I mean, how can we say that for k it is correct? Well, I have one answer for you and that's this. Well, we are assuming that it is correct for n equal to k. We do not need to prove that it is correct for n equal to k. You assume that it is correct for n equal to k and then using that you show that it is correct for n equal to k plus 1. That's it. So we assume that it's a fucking if it is correct for n equal to k, if it is correct for n equal to k, then it is correct for n equal to k plus 1. By n equal to something, I just mean that if n is k, then it is correct. If in here your n is k, this is correct. Then if n is k plus 1, it is also correct. For example, if k is 4, I'm just saying that if for n equal to 4 it is correct, then for n equal to 5 it is correct as well. That's it, okay? So what I can say, I use the power of induction and I assume that it is correct for k. Now my n is equal to k plus 1. So I have this grid of size 2 to the power of k plus 1 by 2 to the power of k plus 1. And I know that one arbitrary cell is blocked. It can be anywhere, okay? It is just one arbitrary cell which is blocked. And I have no clue about where is it. Well, what I can say is that when I have 2 to the power of k plus 1 by 2 to the power of k plus 1 grid, I can split it into 4 subgrids, and each one of them have size 2 to the power of k by 2 to the power of k, okay? So I can say that it is like this, right? And then I can say that I use this shape that I had in here. I use this shape to cover these 3 cells. Okay. I use one of those shapes and try to cover these 3 cells. And then what happens? Can you say what happens then? I mean, I leave it here. Can you say the rest of it? Can you say the solution? Write that in the comments below. I had a 2 to the power of k plus 1 by 2 to the power of k plus 1 grid. I said that it is equal to 4 of 2 to the power of k by 2 to the power of k subgrids. One of them has a blocked cell. That blocked cell is in one of these 4 parts. For the other ones, I will cover one of the cells of each one by one of these shapes. Now what should I say? Say that in the comments below and I will tell you if your solution for that part is correct. It is almost done, everything is done. And guys, don't forget that this was just the easiest way of induction. This was weak induction. There's also another kind of induction named strong. The strong induction, and I will talk about that in the next video. If you are interested, you can watch that one as well. So now I want to play with dominoes. Okay, let's see if we understood induction. I'm trying to... Okay, I'm just trying to use induction in order to be sure that all of these dominoes will fall. If I make a mistake, all of them will fall right now. So as you see, I just care about one thing. If the previous one falls, this one will fall as well. Okay? And that's the exact same thing that we have in induction. We just want in weak induction. We just care about the previous one, and we say that, okay, if that previous one falls, then this one falls too. So all I care here is that I just assume that the previous one falls, and with that assumption, I just show that this one falls too. Oh, I hope that, yeah. For example, I say that if this black one falls, then this green one falls too. Okay, I'm almost done. So I hope, yeah, I think I'm done. Now, if I did everything correctly, all of them should fall. If I made that chain correctly, that if this one falls, then the next one falls. So I just need to push the first one, which is my base. And my step was that I was saying that if this one falls, then the next one will fall. So if I push this one, it didn't work because this part, our chain had a problem. This one was not connected to this one. Okay, I'm not gonna arrange these ones again. You got the idea. See you in the next video. Shaya.